Now, the first question says to us, if x, look at that, it might not be part of this, but you're going to see how your concept of double and compound angles works in this particular instance, right? Number one says, if x is apparently equal to 3 sine of theta, and we're also told that y is basically 3 as well, cos of theta, right? We need to find, right? The examiner is asking us to determine, okay, determine, in other words, determine x squared plus y squared. We need to find the value of x squared plus y squared. This is the first part of the question, right? To me, this looks pretty simple. It starts from grade 8, right? Simple stuff. Substitution. You guys need to understand that most of the things that you're working on here are not news. News is new stuff, right? News. They're not news. It's something that you've seen either in grade 11 or before then. So you should be good at this, right? So what do I see here? This is my solution, right? Most of you might probably have a problem with this, but think about it. They're asking me to find the numerical value of x squared plus y squared, right? So what am I going to do? I'm going to go and say, okay, I'm looking for x squared plus y squared, but x squared plus y squared is something. So then I ask myself a simple question. What is x? I was told that x is equal to 3 sine of theta. Okay, that's pretty simple. So what I'm going to do is in the space of x, I'm going to replace that with 3 sine of theta, and then there's a square there which I'm going to retain. There's a plus sign which I'm also retaining, and there's a y, and the y value is 3 cosine of theta, and also on that particular term we also happen to have a square, right? So this is essentially what I did according to what I'm looking at here. That's basically grade 8, grade 9 work. Substitution, no complications. But what is 3 squared? Now here we might have a problem when it comes to this, because I'm going to make a mistake now. Somebody might write this as 3 sine squared theta, right? People, you got to understand that if you've got something multiplied by something else with some random exponent, it could be anything, right? That exponent has to be shared to the first term, to the first factor, and then shared to the second factor. So it has to be a to the power of n multiplied by b to the power of n. So when I'm squaring here, I can't only square the sine. There's 3 multiplied by sine of theta. So what does that mean? It means I need to square both 3 as well as the sine of theta, right? And if you square 3, you'll end up with 9. If you square sine, you'll end up with sine squared theta, right? This has to be added with what you see there on the second term. It's pretty much the same story. You square 3, you get 9. You square cos, you end up with cos squared of theta. Beautiful stuff. No complications right there. Now, again, I'm going to go back to grade 9 now and look at what I'm sitting with, and remember something very beautiful. The squares identity. The squares identity says sine squared plus cos squared is 1, right? No complications. Very simple stuff. But before I do that, there's a 9 here. So I'm going to apply my algebra from grade 9 of common factors. I'm going to factor out the 9, right? You factor out a 9, you end up with what we call sine squared of theta added with cos squared of theta. But if you see what we have in the bracket, that is as good as 1, because sine squared plus cos squared is 1, and the value of x squared plus y squared happens to be 9 times 1, which is exactly equal to 9. So beautiful question indeed. Thank you for sending it through. Right. Let's go to the second part of this. This one is very exciting. They say to us we need to simplify, right? We did something that was engaging what I call identities. Sine squared plus cos squared is 1. Sine over cos is tan. Full stop. Nothing beyond that. Right. So now I'm going to look at something else very exciting. This is the reduction part now. Right. Let's see what is going on. They say to us here we need to simplify to a single term. Let's go there. Let's go. Simplify. Okay. Simplify to a single term. We need to simplify this to a single term. Okay. Now, when I simplify this to a single term, let's see. What exactly am I simplifying? We have sine of 540 degrees, which is actually minusing x. And then that has to be dotted or multiplied with the sine of negative x. And this is simply subtracting the cosine of something beautiful, which in this case happens to be 180 degrees minus x, and this is multiplied with the sine of 90 degrees, right? Plus x. Okay, cool. Now, what's the theory behind this? What's the theory, right? Let's spend some time dealing with the theory around what's going on here, right? Now, these are reduction formulas. What do you need to simplify this? Well, you need the cast diagram. Okay, you need the cast diagram. How does the cast diagram look? Okay, I want to keep this there, right? Let's actually get an opportunity to go to a blank page and discuss the cast diagram. The cast diagram looks like that, right? And if I draw on this cast diagram the values, or if I write the values on far left, we start with 0 degrees and we measure our positive angles anti-clockwise, right? That means 10 degrees lies in the first quadrant, 20 degrees, 30, all the way up to 80 something degrees lies on the first quadrant. And then you're going to have 90 degrees here. You're going to have 180 degrees here. If you come back, you're going to have 270 degrees. And then a full revolution later, you end up with 360 degrees. We know that this is the first quad, right? We know that this is the second quad. And we know that this is the third quad. And we know that this is happening to be the fourth quad. Why is this called the cast diagram? Because in the first quadrant, all ratios are positive. In the second quadrant, sine is positive. In the third, the tangent is positive. And in the fourth quadrant, only cos and its reciprocal happen to be positive. That's why we call it the cast diagram. So you can obviously see in which quadrant when 90 minus, because 90 minus will lie this side. This is going to be 90 degrees minus any value. And then if you come this side, you're going to have 90 degrees plus any value. If you come back this side, you're going to have 180 degrees minus something. If you go forward, you're going to have 180 plus something. And if you go back here, you're going to have 270 minus something. If you go forward, you're going to have 270 plus something. And if you're looking at 360, that's going to lead you with 360 degrees minus some weird angle. It could be anything for that matter. So this is essentially how the cast diagram looks. Now, if you ask me something very exciting about the values of the angles, and for example, you say, in which quadrant does 20 degrees lie? 20, think about it. You're starting with 0, you're going anti-clockwise, so 20 will lie in the first quadrant. But where does negative 20 degrees lie? Where does that one lie? Think about it. If this is the positive direction, where is going to be the negative direction? Obviously, it has to be the other way around. So this is positive movement, and this is going to be negative movement. So if this is my 0 degree line, this will be all my positive angles increasing in that order. But if I go back to 0 and I start looking at negative values, they're going to be going clockwise. So if 20 degrees is in the first quadrant, then negative 20 must definitely lie in the fourth quadrant. Right, come back. Look at this. So 20 degrees might be in the first quadrant, but negative 20 degrees lies in the fourth quadrant. So as a matter of fact, on the fourth quadrant, we don't only have 360 minus theta or 270 plus theta, but we also have what we call negative acute angles will all lie in the fourth quadrant as well. So please keep that in mind. It's very, very important. Okay, cool. Now, the last thing that I also want to say to you is the following. When you're dealing with reduction formulas, please look at me. I hope you guys are watching. Pause whatever you're doing and look at the following. There's 0, there's 90, there's 180, there's 270, there's 360. Now, when you're dealing with reduction formulas, which trig ratios will change your ratio, right, to its co-ratio? There are ratios and their co-ratio, right? For example, sine will change to its co-ratio, which is cosine. Tangent will change to its co-ratio, which is cotangent. And secant, which some of you are not working on, will change to its cosecant reciprocal, right? So which ratios, which values of, which angles, right, which values are going to change the trig ratio to its co-ratio? Think about it. Look at me. If it's going to be 0, 360, or 180, you will not change your trig ratio. Look at my head. 0 or 180, no changes on the trig ratio. You don't change the trig ratio. But if I'm dealing with 90 and 270, 90 and 270, yes, the trig ratio will change to its co-ratio. So as I'm doing my reduction, I'm keeping that in mind. If it's 90 or 270, yes, the trig ratio is going to change. But if it's 0 or 2 or 180 or 360, any ones that are lying on the x-axis, no, the trig ratio will not change. Keep that in mind. Very beautiful way of thinking about it. Okay, let's go back to the actual question. So this question we're dealing with here is absolutely awesome, if you ask me about it. And it's asking us to simplify what we're looking at here. So what I always encourage you to do is analyze the question before you even start working on what you have in front of you, which means I'm going to look at what changes I'm going to apply on this before I even start with the simplification. For example, when I look at the first part, what problems do I have? This 540 is too much. If a number is too much, you are allowed to subtract 360 on it. Negative angles, we know that these lie in the fourth quad because this is actually going clockwise. 180 minus, no problem. This is going to lie in the second quad, right? Okay, and 90 plus, I've got a problem with 90. That means we're going to change the ratio. We're going to change to cos. So there's nothing wrong with you spending. This is a question that could be worth 7 marks, right? So that means you've got over 7 minutes to think about it. So there's nothing wrong with you looking at it and thinking about what you have in front of you and saying, okay, because there's 90, there's 540, there's 180, there's negative x, what exactly does this mean to me, right? And thinking about what you're going to do before you even start actually simplifying those things. So let's have fun. 540 is too much. It's over that first quadrant. So if an angle happens to be more than 360, which is more than the first revolution, right? You are allowed to subtract 360 on it, and it actually takes us back to 180 degrees. When I do 540 minus 180, minus 360, I'm getting 180. So this question is as good as sine 180 minus x, right? It's as good as saying 180 degrees minus x. In which quadrant does 180 minus? 180 minus lies in the second quadrant. And in the second quadrant, sine is positive. So the simplification of sine 540 minus x leaves us with exactly sine of x, a positive sine of x, because 180 minus lies in the second quadrant. Now, sine of negative x, negative angles lie in the fourth quadrant because they are a clockwise way of looking at angles. And then in the fourth quadrant, if you think about it, in the fourth quadrant, the only trig ratio that is positive in the fourth quadrant, if you think about it, right? Let's go back and check the fourth quadrant. The only trig ratio that is positive in the fourth quadrant is cosine. That means the sine of an angle that is negative will simply be negative since it is actually in that particular quadrant. So please be careful of that. Very, very important. So the sine of negative x is going to be as good as, I'm going to put a multiplication sign here, times negative sine of x, right? Okay, we've got a minus there, and there's cos 180 minus. This is the second quad. In the second quadrant, cosine is negative. So I'm basically sitting here with something which I'm going to call negative cosine of x, right? Multiplied by. Now, the last factor is sine 90 plus x. Like I said, 90 plus, you're going to change your ratio to cosine. So this is going to be cos of something, right? It's going to be cos of something where something happens to be x. The question is this going to be negative or positive? Now, you look at that quadrant. 90 plus is second quad. 90 plus is second quad because 90 degrees is here. So plus is going to be forward, moving forward, which means it's going to lie in the second quadrant side. You look at the question. Don't look at the answer. Look at the question. We know the question is sine and the sine is cos, but you're not interested in cos. You're interested in what is the question. So the question is sine. So in this quadrant, sine is positive. That's why I'm going to end up with a positive result. This is going to be a positive result. That happens to be cos because it's changing thanks to 90. Right. Okay, cool. And we simplify this further. What we end up with, sine times sine is negative. Sine squared of x, negative times negative is positive. Cos times cos is cos squared of x. So I'm going to factor out a minus. So I'm going to factor out a minus there, and I'm going to start with cos. So this is going to be cos squared of x minus sine squared of x. Now, this is where grade 12s start having fun because this must look familiar to you. If I multiply, okay, I think I actually made a flaw there because if you multiply sine and sine, you're going to get negative sine. And if you multiply negative and negative, you're going to get positive. It's cos times cos, which is cos squared. So it actually turns out that I don't need to do this factorization because it's not going to lead me to where am I going. Where am I going, by the way? I'm going to just change the order. Cos squared is positive, so I'm starting with cos squared. X minus sine squared, which is also happening to be negative in this case. So I'm going to have negative sine squared x. And this is not a square's identity, but is a double angle of cos. So this is as good as cos 2x. And if these people wanted us to actually express this as a single trig ratio, we have actually succeeded to do exactly that. The answer to this becomes the double angle of cosine. No complications, absolutely exciting there, right? The next question is also very nice. It's asking us something very nice. So this is number 3, which happens to be the last part of what you're looking at here. They say in the diagram, okay, in the diagram, we have something very nice happening. There's a particular point, T with coordinates x and P is a point on the third quadrant, and it is given that sine of some angle alpha is equal to P divided by the square root of 1 plus P squared. Oh, beautiful stuff. This is what we call solutions of RETs. People who've been observing the 7 wonders of trigonometry. Right, 7 wonders of trig. We are dealing with the third quad. So I'm going to actually write what we have. We've got point T with coordinates x and coordinate P. Very concerning. They are happening to appear positive, both of them x and y, and we know in the third quadrant both x and y need to be negative. Beautiful stuff. No complications. So where are we starting counting our angles? We start from the positive x-axis, we go anti-clockwise. So that's actually alpha. Okay, cool. Now how do you deal with these kinds of questions? Well, we need to complete the ret. What do you call this? A right angle triangle, by constructing that particular line that goes to the x-axis that forms a very beautiful right angle triangle for you, which you would need to now label, right? So according to this, the x coordinate is P, so I'm going to start putting values. So this is P, the x value is x, so I'm going to put this as x, and according to the examiner, we are going to have P as y, x as x, and we don't know what is the length of the distance from the origin all the way to P and to T. So that's actually OT, right? So it's a point in the third quadrant. It is given that the sine of alpha is P divided by the square root of 1 plus P squared, right? So, okay, cool. We see what is happening here, and we don't have any problems with what we are dealing with, right? So, let's first of all see why did I actually do what I did here. It's important for us to understand why did we do what we're dealing with here. Think about it. We are dealing with a situation where the sine of alpha is P divided by the square root of 1 plus P squared. Now, if you think about it, right, what you're looking at on the numerator, because from definition, as far as grade 10 is concerned, from our knowledge of SOHCAHTOA, it comes from as way back as SOHCAHTOA, which is the actual definition of these trig ratios. By definition, sine is the opposite side divided by the hypotenuse side. So this would be the opposite side, and this would be the hypotenuse side, right? Now the first question is asking us to show that the value of x is equal to -1. They say to us here, we need to show that x is -1. That's what we need to do, right? Number 1 here, show x is -1. Show x equals to -1. Okay, cool. So what do we do here? What am I going to do? I'm going to go back to the diagram, right? And think about what I'm looking at. Think about what I'm looking at. As far as this is concerned, right? Sine of the angle must be the opposite side divided by the hypotenuse side. So from sine is opposite over hypotenuse. If we think about it in the context of y as an axis, this would be your y, right? And this will be your r, right? Y over r will be your sine. So which means from the given statement, I can simply come here and find the ray OT, which happens to be the hypotenuse of my ret, and write it down as the square root of 1 plus P squared, right? We've got the square root of 1 plus P squared. The opposite side is P. We are looking at it and we're happy to see that. And we need to show what the value of x is. We're actually trying to figure out the actual value of x. So I'm going to apply my old friend that I know from a long, long time ago called Pythagoras. What did Pythagoras say? I was there when Pythagoras said x squared plus y squared must equal to r squared. Be kind to acknowledge that this information comes from Pythagoras. We're looking for x. So x is x. What is y? The y value is p, so I'm putting p squared here. And my r, I've got a bracket there. My r is the hypotenuse of the triangle, which is the square root, beautiful people, of 1 plus p squared. Okay, cool, close brackets. But there was a square in my question, so I also need that. Legends have it that the square will kill the square root, which means we're ending up only with 1 plus p squared on the right hand side. And if I subtract p squared on both sides, I end up with just x squared is 1, right? But we're not looking for x squared, we're looking for x, so we need to find the square root on both sides. If I do this, I made a mistake. I can hear someone from Northwest saying to me, say, you forgot plus minus.